Okay. So this is something that you would have talked about in college algebra, maybe, but in pre-calculus, definitely. I'm not really looking for a formal definition. I want it to be more intuitive. But you certainly, if you don't remember the precise sort of definition of what it means for a function to be increasing, decreasing, or constant on an interval, you at least have hopefully some intuitive notion of what it means. So if a function's, let's say that, say this is my interval, the interval from here to here. It could be open or closed, I don't care. Let's say open now. If the function's increasing, the graph does what? It rises, it goes up as you go from left to right. If it's decreasing, then it falls. And if it's constant, then it doesn't rise, it doesn't fall. It's just a horizontal line segment. That's really all you need to know. You need to have a picture in them, yes.
What if you've got like a top part of a parabola where it goes up and then down on that same interval?
Well, then on one interval it's increasing, and on the other one it's decreasing. Yeah, so there's no guarantee. What I'm saying, actually, we're just addressing, what it means for a function to be increasing on an interval. It's true that if you were to maybe take this function and look at it in its entirety, that it's going to be decreasing somewhere else. It might increase again somewhere else, and that's certainly going to happen more often than not. But the idea at this point is just that you have an idea, some sort of intuitive notion of what it means for a function to be increasing or decreasing. All right, so theorem, important theorem. Really three statements rolled into one. So you have some functions defined on either open or closed interval. Typically we'll work with open intervals. And suppose that the derivative is positive, or in the second case negative, or in the third case 0. every number in this interval. Then f is, you fill in the blank. Think about this. If f prime is positive, if the derivative is positive, that means that at any particular value of x, the tangent line slopes upward. If the tangent line is sloping upward at every point over the interval I, then the graph has to be doing what? It has to be increasing. What if f prime is negative? And that means that every point on the curve, the tangent line is sloping down, falling, which means the graph has to be falling, which means the function has to be decreasing. And there's only one thing left over, so. So this is an application of the derivative. We can use the derivative to determine where a function is increasing, decreasing, or constant. That's actually going to help us sketch the graph. We have to do it from scratch. We can use the derivative to determine where the function is increasing, where it's decreasing. When we know where it's increasing and decreasing, then we can also determine what where the relative extrema occur and what the values actually are. Let's start with what's this? Determine this function is increasing or decreasing. Well, the first thing you want to do, because we're going to use this theorem, right? We're going to take the derivative and figure out where the derivative is positive, where it's negative, where it's zero is zero on an interval anyways. And once we know where it's positive, where it's negative, then we know where the function's increasing or decreasing. So it starts with the derivative. Now, if I want to know where the derivative is positive and where the derivative is negative, I first might want to figure out where it's equal to what? Zero. Zero is what separates positives from negatives. So set this derivative equal to 0. Factor, if it can be factored. Or actually, yeah, really factoring is the best way to go if it can be factored. Of course, you can use the quadratic formula. Well, if this factors, the factorization is going to have to look like this. Let's see, we're thinking 5, 1 plus, does that work?
Yeah, that should work.
Sure seems to. So you set each factor equal to 0. So these are the numbers that make the derivative equal to 0. Let me ask you a trick question. Is this function constant at x equals 1? Remember, it's a trick question. Well, this theorem says that if the derivative is 0, then the function's constant, right? Well, look at the fine print. This says if f prime of x is 0 at every number in some interval. You can't, it doesn't make sense to say that a function is constant at a point. Do you understand what I'm saying? When you say that a function is constant, or increasing, or decreasing, you have to specify, or you should specify an interval. It's increasing on the interval from 1 to 3, for example, or it's constant on the interval from 2 to 4. Constant at a point doesn't really make any sense. Constant on the interval, yes. Constant at a point, no. So we're not going to say it's constant here, it's constant here. We're only using these numbers to figure out where the derivative is positive and negative so that we can finally say the function is increasing or decreasing here and here. So mark these, sum was negative 5/3, negative 1 2/3. So we're going to chop up the, you've seen this done before, probably, when you solved quadratic and rational inequalities, polynomial inequalities. What I want to know is, for example, to the left of negative 5/3. Pick any number to the left of negative 5/3. Okay. Plug it into the derivative. You can plug it into either version, the factored or unfactored, whatever you think is easier. You plug in negative 2. Is the derivative positive or negative? I'm hearing a mixture. I'm hearing positive and negative. It can't be both.
Positive 3.
Huh?
I'd like positive 3.
So for those of you that think it's negative, double check. Plug in negative 2. Well, let's say you plug in negative 2 here. That's negative 6 plus 5, right? Negative 6 plus 5 is negative. So this is negative. You plug negative 2 in here, you get negative 3. When you multiply two negatives together, what kind of number do you get? Okay, then you pick something between negative 5/3 and 1. Like 0 is the best choice. And you see that when you plug 0 into the derivative, you see that you get a negative result. And don't assume that the sign pattern is always going to change, because it doesn't. But if I were to pick something larger than 1 and plug it in either here or here, what kind of number do I get? For example, if you pick 2, this is positive, positive times positive, this positive, done. Now, what does this tell me about the behavior of the function f? Well, it tells me on this first interval that it's increasing, then decreasing, then increasing again. Remember, wherever the derivative is positive, the function's increasing. Wherever it's negative, the function's decreasing. Yeah.
If it's going from positive to negative, isn't it decreasing on the interval? Like it's above 0 on the left side of that, right? And then as it comes this way, isn't it going towards 0? Or am I?
Wait.
It's positive on the left side.
Okay.
It becomes negative. So as it moves from positive to negative, doesn't it decrease?
Yeah, well, that's what I'm saying. It's decreasing on the interval from negative 5/3 to 1.
The values between negative 5/3 and 1 are negative, correct? So that means the graph.
Wait, which values are you talking about? So the values between negative 5/3 and 1. The values of the derivative?
No, the y values for that.
Well, what I'm doing right here is sine of f prime.
You just figured, right there, you're just figuring out which way the
Gotcha.
graph is going.
The derivative, the tangent lines, I'm sorry.
Yeah.
Okay.
So f is increasing on, well, two intervals, minus infinity to negative 5/3, and also 1 to infinity. And then f is decreasing on the interval from negative 5/3 to 1. So it's doing something like this. It's increasing, then it decreases, then it increases again. You see that? That's what the graph is going to look like. And of course, I didn't ask for this, but I will in the next example. Once you know this stuff here, you know where it's increasing and decreasing, and it's a polynomial function, then we have a relative max at this point and a relative min at this point, don't we? So that's coming next. We're going to take a break.